chemical reactions. I don't know if you liked chemistry when you were doing chemistry back in high school. I didn't. But do you know what? I've taken an approach to, and chemical reactions really is based on chemistry. I mean, if you were doing a degree in chemical engineering, that's going to be a massive chunk of what you will learn. And so, at some point, in fact, I've had 3 PhD students in the past couple of years with chemical engineering departments, and majority of them have been around chemical reactions of some sort. And so it is an important aspect of thermodynamics. Without having that knowledge, you can't really claim that you have enough thermodynamic knowledge, and so we've managed to fit that in the schedule for this unit, and so hopefully you will learn about some of the key aspects of what we mean by chemical reactions. Anyway, objectives are there. I want to start off with the applications, because as you know, I tend to make examples and refer to lots of industrial examples of whatever we teach you, because ultimately that's where you're going to be applying your knowledge to. And so it's vast, really. I mean, when you look at chemical reactions, you may not think about them as sort of an immediate thing that will come to your mind, but energy obviously is massive. Energy is the biggest by far, not only in terms of chemical reactions, but as an industry, it is massive. And in fact, it's going to be growing exponentially over the next decades. Manufacturing, medicine, pharmaceutical, etc., these are all obvious choices. Agriculture, actually, when it comes to the compounds, chemical compounds, etc., that is, again, chemical reactions and processes. Environmental aspects, one thing which is obviously is going to be a big challenge for your generation, obviously, is going to be environmental aspects and climate change. And so if you look at, for example, air pollution, purification, carbon capture, and storage, these are all based on those chemical reactions that we were talking about. Okay, so again, a very important part of our study. And then even less industrial scale, everyday use of things that you would use. Again, there's a chemical reaction in there as well. But I'm going to focus more on the energy and mainly combustion. And the reason for that is combustion by far is, the landscape is changing, obviously. My last slide today will be on the future of combustion. But it's probably the one that is responsible for the biggest amount of innovation in transport, in terms of power generation and so on. So it's natural to think about combustion when we think about chemical reactions. And so also in engineering, mechanical engineering side of things, combustion is probably the one that would attract a lot of interest in different forms. So when we talk about combustion, naturally the first thing you think about is the fuel. So, and the fuel itself is such a massive industry, as you know. I mean, we think we are moving away from oil and gas. In reality, it's not going to be anytime soon that we can remove our dependence on oil and gas. I don't want you to think about oil and gas just in the form of, you see an EV, electric vehicle, and you think, oh, actually, it's phasing out. That is a small portion of the use of oil and gas. When you think about all the different cosmetics, all the different products that we use on a daily basis, majority of them originate from some of these byproducts of natural gas and oil that you extract from the wells, etc. If you look at the crude oil, so you've got gasoline, kerosene, and so on, which is the fuel for airplanes, cars, etc. We know about this. But also when you think about the natural gas, then we've got a combination of methane, ethane, propane, and so on that we use, again, for a number of different applications. I will mention some of these in more detail later on. But the common factor between those fuels and the gases are the term hydrocarbon, because as the name suggests, you've got hydrogen and carbon in the form of, as you can see there, I need to switch on the pen in here. So this sort of form, which shows a number of atoms for carbon and hydrogen, is the default formation of your hydrocarbon in terms of fuels. And it's actually quite easy, because I will show you a table which shows a large range of, a very wide range of hydrocarbons, and majority of them have that sort of simple form of carbon and hydrogen. The other thing to mention is that hydrocarbons actually could exist in different forms, in different phases, you know? So I don't want you to just think about gas, the gaseous form. You've got solid, coal, for example, and you've got liquid. And so the thermodynamic aspect of those phase changes and so on comes into play when we talk about different phases. So this is a long text, but I'm going to break it down to you in terms of the overall category of fuels that we look at. So we all know about petrol or gasoline and diesel. The scientific composition of these fuels are basically octane and dodecane. Now, I have to say, majority of the hydrocarbons and the fuels that we use, they don't have just one hydrocarbon. It's a combination. But we tend to assume that there's a single hydrocarbon, and I think that's a fair assumption, which makes life a lot easier to understand, easier to process and analyze as well. And less common perhaps, for example, are alcohol-based fuels, which I will talk about them later on around ethanol and methanol. But then, if you think about the gas, the natural gas, the biggest portion is methane. In fact, it's the simplest hydrocarbon. CH4 has a number of byproducts. You might have heard about, for example, the compressed natural gas, CNG. So the compression of these gases is a big business. You know, it requires very powerful compressors, storage tanks, cylinders, and so on, because you need something around 150 to 250 atmospheric pressure, so roughly about 260 bar. And to give you a type of sort of, I don't know, I mean, you may not have any feel for 200 bar, but actually it's very, very strong. It's very high pressure. I mean, 40 bar is the limit of our labs. If you want to go beyond 40 bar, we need special, you know, treatments, special, for example, risk assessments. Not even in the normal buildings, you can't have anything over 40 bar. So that is a high pressure, and therefore they are stored in those cylinders, which are very strong in terms of structural integrity. If you wanted to have it in liquid form, then it will be what we know as LNG, and you need to store it at minus 162 Celsius. The same with, for example, hydrogen. I mean, you hear a lot about hydrogen as one of the candidates for the future energy sort of crisis, and again, you're looking at about 180, minus 180 Celsius in order to have hydrogen in the liquid form. So if you think about the logistical aspects of storing a gas or a fuel at those very low temperature or high pressures, that is a big problem. You know, when you think about the transport of these gases, pipelines, when you think about the risk of combustion, and so on. So you will see the challenges that we are facing when it comes to these hydrocarbons. And then, a lot of these gases have been used for even transport. For example, roughly about 1 million vehicles, mainly public transport sorts of vehicles, are using some of these gases, especially LPG, which is the liquefied petrol gas, is the one that is very common. And in fact, not only for transport, but even if you have a sort of a cylinder for a barbecue, you know, that you've seen, that could be actually be propane, which is the biggest sort of gas within the LPG category. So this is one category of fuels based on natural gas, but you also have more of a, what we call like a sort of a green fuels. These are basically alcohol-based fuels, ethanol and methanol, as I mentioned. They, in terms of power and calorific value, they're not as high, but in terms of emissions, CO2, CO, and other emissions, they are much, much better for the environment. Now, they're becoming a bit more common, especially when you are using biomass So I don't know if you will cover biomass very briefly in the next topic when we talk about renewable energy. Biomass, along with, for example, solar panels and heat pumps and other renewable energy sources, wind turbines and tidal turbines, is one of the candidates on the list of things that potentially we have to utilize more often in order to produce power. So when you burn, for example, animal waste or food waste, etc., that is the type of fuel that you could produce in biomass. So there are lots of different ways of expressing and comparing these fuels. An obvious one is just the energy content. So it's not a straightforward type of value because it depends on the purity of the fuel, it depends on the pressure, temperature, and a few other type of parameters, but roughly you will see that there's a vast difference between different gases. In this case, for example, heavy diesel has the highest one. Gasoline probably is the most common one, which means when we want to come up with a parameter such as gasoline equivalence ratio, we use this as a reference. And so you can see that fraction shows where we are with respect to the baseline gasoline. One of the interesting things about hydrocarbons and in general about combustion is the combustion equation. In fact, we will spend quite a bit of time in terms of teaching you and reviewing how you would construct this combustion equation, because balancing out the left and the right hand side of the equation is quite important, making sure that you conserve the content of the fuel and you account for any reactions in that process. So air naturally is the most important oxidizer, if you like, available to us because it's free, you can find it in abundance, and so naturally a lot of the designs for combustion, for chemical reactions, etc., relies on air as a standard sort of gas and oxidizer. Now, as we know, air has a very complicated composition, but the two dominant gases in there are oxygen and nitrogen. In simple terms, the ratio is 79% nitrogen, 21% oxygen, which translates to this magic number of 3.76, which you will see a lot in the combustion equations, because essentially for every kilomole of oxygen, you will have 3.76 kilomole of nitrogen, which will give you the total of 4.76. This number is something that you need to remember. It's not difficult to remember after you do a few examples, but you will see that this number appears in our equations when we construct our products and reactants in the combustion equation. So, something else about, let's talk about moisture, in fact. So, like nitrogen, which is an inert gas, which means it doesn't really react. So, your nitrogen content on the left-hand side of your combustion equation normally transfers into the right-hand side without reacting with a lot of fuels. Moisture is almost the same. The problem with moisture and water content is that if you have water in the content, or moisture in the form of moisture in your air, then what happens is that at very high temperature, it has to be high temperature, you have this dissociation, which I will talk about dissociation in a few slides later on. And what happens in dissociation, that gas, or that, for example, in this case H2O, will break up into its constituent elements, which are hydrogen and oxygen. That is not an issue on its own, but the problem is when the reactants are then cooled down and the temperature of the reactants and therefore the content of moisture goes below the dew point. So remember the dew point temperature that you learned about in the last topic? And the whole psychrometric chart, it's an important parameter. It's all about condensation. That is the one that would define at what temperature, that's a threshold, below which you will get condensation. And if for some reason you go below that dew point temperature, what happens is those water droplets could react with sulfur if you have that in your fuel and in your reactants, which is actually not uncommon. You will get something called sulfur dioxide, SO2. And that is actually quite terrible in terms of having very strong corrosive features which could damage, let's say, the combustion engine, the elements within that combustion chamber and so on. And so the design of not only the temperature and pressure and so on in the combustion process, but also the moisture content of your fuel and air is an important aspect when it comes to high power output and combustion or complicated combustion systems. For example, internal combustion engine is one of those examples of high temperature combustions or reactions. Rocket engines is another example, for example. So these become quite important to get that sweet spot in terms of making sure that you don't have very high moisture content, otherwise you will damage the engine and the components. Now, I want to talk about 3 features of the whole combustion process. One is the ignition temperature. These fuels are combustible, but unless you bring them to the ignition temperature, you are not able to start that combustion process. In fact, that causes a lot of challenges when it comes to the design of engines and so on. But thankfully, these temperatures, which are relatively high, I mean, if you look at the minimum ignition temperature for gasoline, 260, let's say hydrogen, 580, and methane, 630. Now, I mentioned that methane is the most available gas in the natural gas in the world, and so imagine if that 630 was 60 Celsius, right? I mean, the whole world would be on fire. So in a way, that's a good thing that you need to have that minimum temperature, ignition temperature, which is actually quite high. So in nature, you can't achieve that temperature. Otherwise, as I mentioned, these oil gases and gas wells, etc., will be on fire regularly. The other thing is about the air-fuel ratio. So I mentioned air is the main oxidizer. You need the oxidizer for the combustion process. And the ratio is very key. There is a range which could work. And if you go below or beyond that range, you're not going to have the combustion process starting. To give you an idea, for example, 5 to 15% is the fuel-air ratio that you need to have, for example, if you want to have if you want to burn natural gas. And so we will talk about this in more detail later on in terms of the significance of having excess air or less than sufficient air, really. Any questions up to this point? All clear? I'm hoping this is just some basic stuff to remind you of hydrocarbons. Okay. So let's start looking at our combustion equation and the main components and how we count them and so on. So by default, you've got 2 ways of expressing your fuels and hydrocarbons and air and so on, either by mass or by volume. We covered this in the first topic when I was talking about the vapor form and gaseous forms and different gas mixtures and so on. The way that we write our combustion equations are based on volume. So you count the number of moles, which doesn't necessarily have you can't equate the number of moles on both sides of the equation naturally. Because if you've got 1 mole there, 1 mole there, you expect to have 2 moles there, but in reality, this is only 1 mole, okay? So you don't expect to count them and balance them out, unlike mass, which needs to be balanced. So that's the main distinction between the way that we construct these equations. Now, if you look at this very simple balance of hydrogen and oxygen, what will balance out is the number of atoms and so on. So, for example, if you count the number of hydrogen, I've got 1 molecule of hydrogen, the same here. If you multiply these half by 2, obviously you get 1 atom and you get 1 atom there. So that is what balances out on both sides. As I mentioned, air-fuel ratio or fuel-air ratio, that is, as the name suggests, this is around mass. But it also could be based on volume. So it could be the volume of air versus the volume of fuel in the form of number of moles. So the number of moles for air over the number of moles for fuel. So whenever you get a question or a problem on combustion, always look out for, are your numbers given in mass or moles? Because if it's mass, there's a conversion that needs to be done before constructing your equation. As a reminder, we refer to these three parameters, mass, n for number of moles, and the molar mass regularly. And as I mentioned earlier, molar mass is the equivalent of density, which really takes the mass into account. I mean, you'll see here, it's the mass over, if I rearrange this equation, molar mass is mass over the number of mole, which is mass by volume, equivalent to density. So let's do one example, and then this example hopefully will show you how we start counting atoms and molecules on both sides, and we balance them and we work out air-fuel ratio. So we've got octane with air that contains 20 kilomole of oxygen. And that's a tricky bit because we don't have 20 kilomole of air, this is 20 kilomole of oxygen only. Now, we also know the products, and to be honest, even if you didn't, you would expect to have these three default products, CO2, H2O, and nitrogen, but with an addition of oxygen in there, suggesting that perhaps you will have some excess air present in this case. So what you do normally, you will start putting your fuel first, then your air, and in this case, this 20 is a factor which needs to be multiplied by the whole ratio of oxygen and nitrogen, and this is the number which I told you will appear whenever you have air represented in your equation, followed by the four products that you expect to get in your equation. Each product will have its own unknowns, x, y, z, and so on, and then your task is to start counting all those fundamental and basic elements: carbon, hydrogen, oxygen, and nitrogen. You could, for example, have sulfur or other components as well, but in this case you don't, and so you're only limited to these four options. So naturally, by counting them, you then can finalize your combustion equation. In any question that you get on chemical reactions, that is always your starting point. So you should feel absolutely confident in constructing this. This is not difficult, really. I would say the only tricky bit with combustion equations, when it comes to having different type of oxidizers or excess air and so on, the complication normally is around this bit, and maybe about the number of products that you could have on the right-hand side. Otherwise, everything else should be really straightforward by now. Now, when it comes to air-fuel ratio, this is air-fuel ratio by mass, so that's a conversion where I was talking about. You need to know the molar mass of air and the molar mass of the components which refer to your fuel. Thankfully, your fuel actually here is quite simple, and so in order to work this out, we will have n times m, so we have 20 moles of oxygen oxygen and nitrogen, which comes to 4.76, and this 29 comes from here. We've rounded up to 29. It's 28.97, but 29 is a good approximation. When it comes to the fuel, we had 8 times 12, so 12 is for carbon, which is in the table as well. And then you've got hydrogen there as well, which is 9 kilomole of hydrogen or 18 kilomole of hydrogen atom, depending on how you want to express that. Doesn't really matter, it comes down to 18. So in this case, you will find that the air-fuel ratio is 24.2 kilogram of air per kilogram of fuel. It doesn't really matter if it's kilogram or gram or whatever, or pound, as long as you're consistent in your values, and basically you just conserve that those units across the equations, that should work as well. Now this table A1, which has been taken from your appendix, I want you to be familiar with this because this is something that you will be using as well, and it will be given to you as part of your data sheet in the exam. And what you see, although you don't use critical point properties in this context, that is where you would have used these, for example, when you look at them as pure substances or working out the value of Z. If you remember, that was the correction factor for the ideal gas equations that we talked about a few weeks ago. But what really you would be using in the context of gas mixtures and combustion and chemical reactions are these two columns, molar mass and the gas constant. Which again, I think this is relevant also to the gas mixture topic that we had a few weeks ago. Are we okay with this example? Yeah? Easy? Okay, cool. I don't expect any, you shouldn't really expect any problems or challenges within an example of this nature, because this is just a very basic example. Now, I want to talk about the combustion again in the form of what we call complete combustion. Officially, so again, we talked about hydrocarbon as the main composition of fuels. So if the carbon, all of it, converts to CO2, and the hydrogen converts to H2O, and if there is any sulfur, it converts to SO2, then that is considered to be a complete combustion. Naturally, incomplete combustion, which we don't want, it's not desirable, will result in gases and products that are really just either harmful to the environment or pain to take care of and process. Perhaps except hydrogen. I mean, hydrogen is relatively an expensive gas, especially in recent years. But sometimes if you have a small content of hydrogen in your product, the cost of extracting the hydrogen is more expensive. It is much higher, that cost, compared to the value of hydrogen and what you do with it. So I don't want you to think about that in any process. If you have some percentage of hydrogen, that is a good thing. Well, it's good if you can separate it. Again, we've had a project around, I will talk about what we know as syngas, synthetic gas. It's one of those terms that I want you to be familiar with, because you will hear a lot in industry, especially in the chemical industry, and also in the context of chemical reactions. It's the synthetic gas is essentially if you're burning or gasifying a certain fuel or a combination or a waste, for example, and you use steam or some sort of form of moisture, you will have a gas which is known as syngas, which has contents of hydrogen with something else, which could be CO2 or CO, and that, as I mentioned, has an important industrial role to play in a number of industries. I want to talk about three scenarios, if you like, for the combustion. Insufficient oxygen. That is a big problem, especially if you don't design your combustion chamber properly, or if you are operating in a condition where you don't have enough air, or you don't intake enough air because of the design or low density or whatever. That is where what you get, insufficient oxygen. And that is very harmful for the environment, because normally you end up with CO and carbon deposition and so on. The other side of things, which is perhaps lack of design or lack of efficient design of the combustion chamber or the whole chemical reaction process, is about insufficient mixing. So if you remember when you were talked about internal combustion engines, the whole cylinder, the timing of where you would inject the fuel, the shape of the cylinder and the piston. These are all actually are very sensitive to the whole mixing, because if you don't get that right, the timing, the pressure, the size and so on, if you don't get enough mixing of the fuel and the air in the right time, you are not going to have a complete combustion. In fact, you always want to induce some sort of turbulence in order to enhance mixing, because mixing in the case of chemical reaction and combustion is a good thing. Okay? You don't want localized type of combustion happening, because that is just going to damage the combustion chamber and also will reduce the efficiency of your process. The third thing which I want to talk about is the dissociation. I briefly mentioned about dissociation of moisture contents. I want you to imagine dissociation as the reverse of combustion. Okay? So if your if your molecule is breaking up into this basic form or elements, or the constituent elements, that is what we know as the dissociation. For example, let me give you an example. If I write CO2, okay, now I could get that into CO and oxygen, okay? So the CO2, which is a common product in our combustion chamber, or actually even H2O, it could you could get into hydrogen and oxygen in that form. That is, if that happens, that is dissociation. In this direction is combustion and chemical reaction, as you know, which is common to happen. But if it happens in the reverse, that is what we know as dissociation. Now, why do we have to care about dissociation? In high temperature combustion, I'm talking about probably about 2,200 Celsius above. Again, we're looking at high performance engines, high performance or large heavy duty type of internal combustion engines, rocket engines, gas turbines, etc. What happens is that if you get that disintegration of the products such as CO2 and H2O, etc., your temperature drops. So this dashed line is what you would aim to have. Okay? So this dashed line, the vertical dashed line, represents your perfect combustion or the complete combustion line. At that point, if you have dissociation happening, your maximum temperature actually will drop significantly. And that 200, 300 Celsius in this case will mean that not only you will have lower efficiency, but also some products that may not be desirable in your process. So the design of the temperature, the combustion chamber, and the environment within which the chemical reaction happens is quite important to get it right in order to avoid having dissociation. Now I'm going to perhaps, let me just see. Yeah, I'm going to cover this slide and then let's take a break for about 15 minutes and then we'll come back at 12 to continue. So, something about oxygen is that oxygen really likes hydrogen, as you probably have guessed by now. And it's actually, oxygen is quite biased because when there is clearly lack of oxygen in an environment where you are trying to induce some sort of chemical reaction, it will always choose hydrogen as a first choice. That means that if you have any degree of insufficiency of air or oxygen, you will end up with some sort of carbon in the product. Now, this picture, you've seen something like like this probably in different environments. If you have, in fact, if you open any type of internal combustion engine, you will probably, that's a very common image, having the carbon deposition, what we know as soot, which is the sort of essentially the plain carbon deposition on those surfaces, that is one of the reasons. I mean, in theory, you shouldn't really get that in engines. But if you've been having, if you are driving a car and the engine is not, you know, or you're putting too much pressure on the engine, massive acceleration, massive ramping up of RPM and so on regularly, then you perhaps expect to get over time deposition of soot on the components. And over time, that deposition will reduce the efficiency of the engine and of course will impact the completeness of the combustion. So some of the commercial engines, for example, they get cleaned up every couple of years as part of maintenance just to be able to wipe these carbon depositions off. But carbon actually is a big problem, not only in the combustion. In fact, if you look at some of the nuclear reactors in the UK, CO2 is the coolant. In the advanced gas-cooled reactors in the UK, we've got 8 of them in the UK, which is actually exclusive to the UK. You have CO2 as the main coolant. It comes into these channels, essentially, and because of high temperature, high pressure, the first thing you see will happen is the carbon deposition around the elements and around any roughness within the cooling channels. And this has been a problem actually for decades with AGRs. But anyway, I mean, that problem is something which is not exclusive to chemical reactions and combustion. Okay, so any questions? Obviously, feel free to come down and ask me questions if you want to do that. But let's take about 15 minutes break. Please come back at 12 if you want to go outside, and then we'll carry on, okay? So I mentioned that I wanted to talk about the exam paper because there are a few things I wanted to mention, and I think there was a question from one of you just now, which I think is quite important. Because I won't see you again for this unit, so I just want to sort of clarify that. So on our Blackboard page, you will see exams and solutions for the past 3 years. Now, one thing that you will notice, I mean, if I just click on last year's exam, one thing you'll notice is that some of the questions are on topics that you might know, and I think you should know, but they're not from this year's sort of materials. Just to give you a bit of context, so up to this year, we used to have some topics which were complementary to what you learned in year 2, like gas power, for example, advanced gas powers, power cycles, and for example, entropy and so on. And so if you look at these questions, for example, question 1 is around air conditioning, which is fine, you've covered that. In fact, the only 2 topics which are, I'm trying to remember if we had chemical reactions in previous years in this module, but certainly things such as this question here is something that you've done in the last topic. The question around, for example, chemical reactions and so on should be relevant. But for example, this type of gas turbines, these are the stuff that you perhaps covered in year 2. The idea was, in previous years, the idea was that they will build up on what you've learned in year 2, but then provide you with more advanced sort of content. But I made a decision to change that in a way that we will add topics that you may not have covered, and that allows you to have a sort of a more diverse understanding of thermodynamics, because this might be the last opportunity you will ever do thermodynamics, depending on whether you do BEng or MEng, etc. Even if you do MEng, I think this is the last time you do thermodynamics, and so you will hopefully be equipped with a more diverse type of understanding of thermodynamics, as opposed to just drilling down into a certain topic and provide you with more advanced content. So don't be alarmed if you see questions in the past exam papers that do not look familiar to you as far as this unit is concerned. And so I would say, in order to prepare for the exam, your best bet will be to do the tutorials, the examples, and the additional questions that the tutors have been doing in tutorial sessions. They are the most relevant ones. In fact, I would say the exam questions wouldn't be outside of those that we've done. I mean, it's not going to be obviously the same as tutorial questions or examples, but if you feel confident about them, I think you should feel confident about the exam paper as well. Okay? Any questions on that? One thing you could understand from this, from last year's exam paper though, is the formatting. The fact that every question is worth 25 marks, 2 hours, and then the type of information that will be provided to you. I think that is critical. I know I've mentioned this, but if you look at any exam paper, let me start with this one. At the end of the exam paper, there is something called the data sheet, and in fact, this will change now because we've got extra topics such as, for example, renewable energy and so on, and an extraction of Appendix 1. This is exactly what you're going to get in the exam. In fact, your exam paper will be very thick because of these like 30, 40 pages of the tables and appendix, including the psychrometric charts, which will be at the end of this document, for example. Okay? So, the other thing I would mention is that you have 4 topics. I've tried to separate these topics very clearly to make them distinct. You will get 1 question on every topic. So that's very clear cut, and so hopefully you will know exactly what to expect. The other thing is, as far as the data sheet is concerned, if you click on this link, data sheet, the exam data sheet there, that is, I believe, that's the one. You're going to get a copy of this in the exam. So you will see now, for example, this is different to past exam papers because we've got renewable energy, we've got more stuff on specific and relative humidity and so on. So spend some time in browsing through these data sheets, because in the exam you don't want to be looking for an equation. And the question that I always get, do you have to memorize this? Do you have to memorize that? Well, based on what you see here, you will know what you need to memorize. Okay? So let's just move on from that. Are there any questions on what I've just mentioned about the exam papers? I'll be clear on that. Yeah? Okay. So let's just continue with our lecture. So I talked about soot as a carbon deposition that is quite common because of that tendency of oxygen to mix with hydrogen as opposed to carbon. Now, let's talk about, again, going back to the perfect combustion. Let me talk about what we call the stoichiometric. It's an ugly word, the first time I heard it. Stoichiometric combustion. I want you to think about the stoichiometric or the theoretical air or combustion as the perfect amount or exactly the right amount to be able to have a complete combustion. So for any type of hydrocarbon, temperature, pressure, the design of the combustion environment and chamber and so on, there is the exact right perfect amount of air that will be necessary to burn everything. Okay? So, and that is the stoichiometric one. And you know what? In reality, in fact, you will have excess air in most cases, because not only you can't provide a stoichiometric amount, in fact, sometimes because of the limitations that you have in physics, because of the design of the combustion and the environment, even if you provide the perfect amount of air, that may not be sufficient at times. And therefore, it's a very good and common practice to provide excess air by certain percentage, 5%, 10%, etc. In fact, we are at the moment doing one project with a company that are designing an oxidizer. So you need to treat certain gases, after burning something. They are recycling. This is the biggest site in Europe for recycling tires, and so for environmental aspects, they need to treat the gas. And so we are designing this oxidizer, and for that, in order to burn the fuel and the syngas properly, we need to provide around 5-6% excess air. I think that actually completely changes the whole performance. So as you know, I'll open a bracket here to talk about how we would do stuff like that, just to give you an idea. So you know about CFD, and you know the capability of CFD, what CFD can capture. The CFD for a combustion chamber is quite common. You will model the combustion, the flame, you will incorporate some equations for the chemical reactions and so on as an add-on equation, because these are extra equations that you need to solve beyond the Navier-Stokes. But then, when it comes to chemical reactions and to, when it comes to the design of how these gases will react together and products and so on, we have a different method called process simulation. Process simulation is not something that we normally do in our degrees in mechanical engineering, but actually equivalent of CFD almost for chemical engineers are process engineering. So a program like Aspen Plus, is something which is very commonly used. In fact, sometimes for us, sometimes we use Aspen in conjunction with CFD programs. And in order for you to be able to decide on how much excess air you need and what products you get and what kind of content you get in your syngas, process modeling is the one that you need to do, with such as Aspen and other programs out there. So just bear that in mind, that there are lots of other simulation techniques that are well established and are very useful and actually not completely irrelevant to what we do in mechanical engineering. One of them is process engineering. Process simulation. Okay, this graph is actually quite interesting because what you see is that this vertical line, this one, shows that it's stoichiometric combustion. On the right, it shows excess air. To the left, it shows excess fuel. Okay, so we don't want excess fuel, really. In some processes, we do need excess fuel. Like we're talking about applications which are like aerospace applications, some of the jet engines and rocket engines, etc., where you're not really bothered about long-term efficiency or the environmental aspects. Elon Musk doesn't think about environmental aspect when they think about the design of the SpaceX, for example. I mean, these are exceptional cases, right? But when it comes to normal applications of combustion, then I think it's quite important to think about efficiency and cost. And so you see here there is a narrow window which will give you the highest efficiency, and in this case, for example, is between 1 and almost 2% excess air. And these lines correspond to CO2, CO, and the composition of the fuel at different levels. And you will see, if you don't have excess air, you will end up with massive amounts of CO, massive amounts of CO2. But if you are operating, and I think this one doesn't show the efficiency, but efficiency actually completely changes when you are within that window. And so I think this is something which I want you to think about when you think about the chemical reactions and so on. On the other hand, we've got lack of sufficient air, which happens perhaps not on purpose, but because of poor design, poor conditions of operation, and so on. Okay, so as I mentioned, it's natural to have excess air. I mean, in the case of, this is 50%, 200%, but this is 90%, which means 10% deficiency of air. Whatever that is, that will constitute itself in the factor that you put in here to correspond to the air. And this is why I said this part of the combustion equation is probably the trickiest part, because that's the part where you need to account for excess air. You need to make sure that if you are doing theoretical combustion, that is covered and so on. So that's the idea. In terms of composition, I mentioned that with process simulation software and so on, you can predict and do some calculation in terms of what will be the composition if you have this fuel and this air, and you put them together under this environment, this is what you get. But in reality, if you want to really get the exact composition of a certain gas or fuel or something like that in a real combustion or chemical reaction type of environment, you would use, nowadays you would use something like this device, which is the ORSAT gas analyzer, which would actually, this is a non-dispersive technique because it uses infrared, so it doesn't need to have any contact with the gas, which is quite good because sometimes they could be toxic, high pressure, high temperature, and so you can't just put a thermocouple in there, or you can't just put a sensor in the environment in order to be able to measure something. And so these are quite good, and they come in different ranges, as you can see here. Within ppm, particle per million, which is a common unit, obviously, as we know, for concentration, and so the higher the range of concentration that you can detect, the more expensive and more sophisticated this device will become. But the name ORSAT comes from this type of experiment, which used to be the way of extracting and deciding what is the composition of certain gas. And what it does, or what it used to do, using a number of agents, or chemical reagents basically, what it does, different reagents actually would absorb certain gases. And so if you do it step by step, let's say this is your gas sample, which includes CO2, and the volume is 1 liter. If you then introduce some sort of reagent in here, which will react with CO2, therefore absorb CO2, and then you measure the volume again, and you realize the volume now is shrinking to 0.9 liters, you then know that you've got 0.1 liter of CO2. And if you do it step by step, you will then have the composition for the gas. But that is a tedious, expensive process, and therefore these infrared type of sensors are a lot more effective. Okay, a long example here. Let's try to go through that very quickly. The reason why it's so long is because there's a number of, we need to do a number of conversions between mass and mole. If you read the question, we've got coal from Pennsylvania. I don't know why it matters where it comes from. We've got, these are all compositions given by mass. So 84 something percent carbon, hydrogen, oxygen, nitrogen, sulfur, and then some ash. Now, the ash, it already says it's actually not going to react, it's non-combustible. But actually it's something that you may have to account for in your analysis. Now, because you need to construct your combustion equation, you need to use this generic equation which I've given you earlier, which would relate the number of moles which we are after based on the mass. So naturally, you just put the mass that was given to you in the question, you find the molar mass from the tables, or if you remember them, some of the common ones you should remember, and then you get the equivalent kilomole. And these are what would then go into your combustion equation. But the question really here is, what is that theoretical amount of air that you need to have a stoichiometric condition? So this ATH is that theoretical air, or the stoichiometric air, that you need to find. And so the only way to do it is by start essentially counting the number of atoms and components that you've got, and then using simultaneous equations, you will then be able to work out what is that exact amount of theoretical air that you need in order to have a complete combustion. Now, I want you to understand very well this process, okay? Because as I mentioned, this is easy, tedious, but it's necessary to be able to construct your equations. And then, what we need to do is, we need to find the air-fuel ratio. Now, in order to have the air-fuel ratio, by mass, we need to do another type of conversion, converting it back from moles to mass. And that's what we are essentially doing in here. But before doing that, what we do, we want to find out for the products, okay? We need to find for the products the percentage of each of those different gases, CO2, hydrogen, SO2, and nitrogen. So it's just a normal percentage, really, a fraction. This is 90.63%. This is, let's say, 2.6%, and so on. And that allows you then to work out the equivalent or the apparent molar mass for the products. So the capital M, which is the molar mass, we could get that for basic gases like hydrogen, oxygen, etc. But for this specific type of product, there is no table to get that. And so the only way to do it is by doing this calculation, which we know as apparent molar mass or the equivalent molar mass for the product. And so the last thing, as I mentioned, was the air-fuel ratio, and the air-fuel ratio is basically just multiplying the mass of the air. This comes from here by 29, which if you remember, 29 was what we found from table A1, which was for air, which we did in the previous example. And of course the mass of fuel, by assumption, is 100 kilogram, because we just assumed it's out of 100. Does it make sense? Yeah? Okay. Now this one is interesting, because this in a way taps into what you learned in the previous topic, which was about vapor pressure and moisture and so on. And so what we do in this example, the question is raising the this issue of moisture and how we deal with moisture content in air, which we've so far essentially ignored, if you like. Now, because we haven't ignored, we assume that the air is dry, what you provide to your combustion. Now, of course, as you know, the relative humidity of air could change completely. In this room, potentially it could be 65, 70%. In a desert, in Saudi Arabia, it could be, let's say, 5%. And so the moisture content, where you're operating that combustion and process and chemical reaction really matters when it comes to the equations. Now, here we have natural gas. Thankfully, we have volumetric analysis. So 72% methane, 9% hydrogen, 14% nitrogen, oxygen, CO2, etc. And now we are burning it with air at 20 Celsius, 1 atmospheric pressure, and 80% relative humidity. The question really is, how do we account for that relative humidity? Because we haven't done that yet. And so this is what we will deal with. Now, the first thing you do, as just we saw in the previous example, is to work out or construct your combustion equation in this form. Now, one thing you, of course, by balancing this out, you will get is the theoretical air that you need, which is fine. So you now have everything to be able to develop a nice, or write up a nice equation for the combustion on both sides. But then, the question really is, we had some information there, 20 Celsius, 1 atmospheric pressure and 80% relative humidity. How do we use that? If you look at the table which we used for the previous topic, and in fact in year 2, is the saturation pressure for water. So what is the saturation pressure for water at 20 Celsius? Is this. Now, we need that number because this is an equation for relative humidity, and we've used this very often. This is an equation that you will be using actually in topic 2. We know this is 80%. We know this from table A4, and what I need to do is find out the vapor pressure for the moisture. Then there is this ideal gas equation that I need to construct, because what I'm trying to do, I'm trying to relate the pressure ratio to the number of moles. So we all know PV equals nRT. A lot of these will cancel out, and what you're left with is N and P. And so there's a very nice ratio between the number of moles of air over the total number related to the pressure ratio. We have the pressure thanks to this, and thanks to the fact that we know it's 1 atmospheric pressure. So it's 101 roughly kilopascal. What you need to do is, you've got the number of moles essentially, for air appearing on both sides. So with some simplification, you will work out, which this works out to be 0.131 kilomole. Now, how do we account for that? Where does that number go? That doesn't go on the left-hand side of the equation. That doesn't change really. Where it ends up, it will end up in here. Because the moisture content, if you assume that it's not reacting with anything, it will just transfer to the right-hand side. And therefore, as opposed to having something which was originally the value of y, which was, how much is y? 1.53. Now I'm adding 1.53 to the new number which I found, 0.131, and that's my new updated value for water. Okay, and now what I need to do is, I need to do the same for the products. So it's the same ratio, but now I'm using the products. By doing that, and I've given you some instructions in terms of, you know, where these numbers come from. Obviously, you're adding up these numbers to get the number of moles for the products. I just want to clarify that. And so once you get the pressure, the vapor pressure, you can then find out from the psychrometric chart what is the dew point at that pressure. Again, this is, by now you should know how to use that and get that, because the last topic was about psychrometric charts. So anyway, this is what we get as a dew point. Now, to give you a bit of context, so had you assumed that you had a dry air as opposed to air with 80% relative humidity, your dew point would have been 59.5, so almost 1.4 Celsius difference. Now, you may say, well, really, I mean, for 1.4 Celsius, did we have to go through all this trouble of dealing with vapor pressure and so on? Now, I'll tell you something. So, when it comes to, this is not relevant to chemical reactions, but when it comes to the last topic where I was talking about the hybrid coolers and evaporations and, you know, and cooling systems, 1, 2, 3 degrees could actually make a huge difference. Because, you know, don't take that lightly. I mean, you know, even 1 or 2 Celsius actually could be an important factor. That could mean a much bigger component you need to account for that extra temperature and so on. So, of course, in some of the industries, this may not be as significant, and I understand that, but 1 or 2 degrees in this sort of area actually could be significant. So, I think, you know, this just shows that accounting for the moisture, perhaps, when the relative humidity is high, is an important aspect. Okay, so having said all those, I need to give you a caveat about this. Now, in reality, for analysis of this nature, you would rarely use hand calculation. Okay, I mean, I don't know any industry that wouldn't use some sort of software or automated calculations or correlations to work out some of these parameters, the dew point temperature and so on. However, just like CFD, FEA, any type of simulation technique that you've learned, if you don't know the fundamentals of the equations, you will just treat that software as a black box, and that's quite dangerous. Okay? You don't want to be sitting in a plane which has been designed by CFD engineers that don't know the fundamentals of Navier-Stokes equations, right? So it's the same thing. You've got to understand the fundamentals to then be able to use the software more effectively. And that's exactly the case and why you are learning about these things. So let's now dig into a bit of a physics, really, of chemical reactions. Before I go through the last few slides, are there any questions so far about the examples we've just done? Do you all feel confident? Yeah? It's not too difficult? Yeah? Okay. So the atomic structure of substances that we deal with in nature are fascinating. You know, I mean, you can't even imagine that within the core of a certain gas or a certain component, there is such huge amounts of energy available. I mean, if you look at nuclear energy, fission, fusion, it's incredible how much you can get out of them. Even hydrogen, you know, hydrogen bombs, for example, or hydrogen reactions that you may have read about in the past. You know, they are extremely powerful in terms of the amount of energy that they will release when you break this bond. But what I just mentioned is about the nuclear energy, which is beyond the scope of this topic, right? We don't want to be talking about that really. There are two other, if you like, areas that are relevant to engineering. Of course, nuclear energy is also relevant, but as far as the chemical reactions are concerned, excluding the nuclear energy, if you look at the whole system, you've got two main components. One is for the state, the other one is the chemical structure, the chemical reaction. If I look at the interaction of two molecules, let's say this image here, what happens is that there is a bit of chemical bond between the molecules, which would lead to what we know as latent energy. And so when you are, for example, evaporating water or freezing water or whatever, that phase change, what we know, and actually absorbs or releases a lot of energy, that actually is something which would go towards that latent energy. You also have the sensible energy, which means the more heat you give to a fluid, the more energy it will contain. That's a sensible energy, and we know that in the form of temperature. But the other one is a chemical energy, which is within the boundaries of the molecule, okay, which is building up on the intermolecular forces and the atomic structure of that molecule. So, after doing a chemical reaction, if the reaction within the chamber, if the inlet state of the reactants becomes the same as the condition of the products, then it means you're not really changing anything within the sensible or the latent heat. Which means if there's any change, it will be because of this component. So this one essentially becomes not relevant as long as you maintain the balance between the inlet and outlet of the chemical reaction. And so that really is the chemical components of that reaction. So one of the challenges is that when it comes to chemical reactions, it's just a very diverse type of fuels and air and temperature, operating pressure, design of combustion and so on. Even within the hydrocarbon, we've got, as I mentioned, different purity, different combinations of hydrocarbons, etc. So we need some sort of common ground. We need some sort of reference. One reference that is quite common in chemical reactions is a 25 Celsius or a 77 Fahrenheit and 1 atmospheric pressure. This is the standard reference state, which means we then define them with the simple superscript circle, and in fact, within this context, that circle represents standard type of standard state. So whenever you see this, it means is the enthalpy at 25 Celsius and 1 atmospheric pressure, which then means that for any type of gas or any type of fuel, etc., let's say nitrogen, if I find the enthalpy for nitrogen at 500 Kelvin minus H circle would be this amount. And this amount now is tangible because of using this reference. And in fact, now we could start providing a table which would give this delta H, if you like, for different gases at different pressures and temperatures. two very important terms that you may have used or have learned about are exothermic and endothermic. Very important, very critical, two separate categories when it comes to chemical reactions. When you are in combustion, I mean, combustion generally is an exothermic process. It releases heat and energy. In a lot of propulsion systems, a lot of systems that we deal with in mechanical engineering, majority of them are exothermic. However, there are numerous applications where you will have endothermic, which means in order for the reaction to happen, you need to provide the heat, sometimes significant amounts of heat, which is sometimes, you know, I think it may not make a lot of sense. But actually you will see, I will give you one example later on where you will see that endothermic reaction is quite critical in a number of industries. One of them is what we call steam reforming of methane. In fact, let me just explain that here. So, believe it or not, steam is such a big player in chemical reactions and actually in chemical industry. In fact, there's a big company, Spirax, I don't know if you know them, they are in FTSE 100, it's a massive company, 10,000 employees and so on. All they do is just steam generation. They're one of our partners in some of our projects, and so their expertise is just providing steam or designing components that will provide and generate steam. And if you wonder where would you use steam, well, one of them is steam reforming of methane. So methane is this gas which is available everywhere. It's, you know, it's the biggest portion chunk of natural gas. And what you do with this is, if you imagine CH4 is methane, if I expose that to steam, which is H2O, I could get, let me just write it here, I could get CO plus hydrogen, essentially. Okay? This is exactly the same gas which I was referring to. Now, what do you do afterwards? You take CO, you then expose it to more steam, so this is H2O. And what you get is, you get CO2 plus hydrogen. So, this wasn't that great. CO2 is much better. You have 2 rounds of what we call steam reforming of methane. And what you end up with huge amounts of hydrogen. So if you are looking to generate hydrogen for energy purposes, for whatever purpose, steam reforming is one of the applications. If you are after CO2, in fact CO2 actually has a lot of industrial applications, again, steam reforming is one of them. And so you will see exactly how, you know, and my point of saying this is that these are endothermic processes. Okay? And so you need to provide that energy for this reaction to happen. Hence, you never have that steam reforming for power generation or propulsion. Anyway, so one thing I want to mention about this slide is that if you take CO2, if you provide 1 kilomole of carbon and 1 kilomole of oxygen and make them react in the combustion chamber, what happens is that as it forms CO2, it would release exactly this number of kilojoules because it will be an exothermic process. So CO2, this common gas, surely this number should be of significance. We should be able to give this in a table, the same with other similar gases, and then use that in our calculations. In fact, we do. And what that corresponds is that, you know, we as you remember, so this is just in terms of energy, but the enthalpy change, what we call enthalpy of reaction, is a value which you will be able to find in tables, which would give you the enthalpy difference between the products and the reactants. And that's a number that you can find in tables. The difference between enthalpy of reaction and enthalpy of combustion is that this is more generic. Doesn't really matter if it's exothermic or endothermic. Whereas this is for combustion, and therefore these are the gases which are mainly exothermic. There are two limits, though, to the whole enthalpy formation idea. And I alluded to this one earlier. Now, there are so many fuels and fuel mixtures and so on, you can't just possibly list all of them. You can't just list HC for every single scenario that you could encounter. The second thing is that you can't even assume that the combustion process will be always complete. In a lot of scenarios, it will be incomplete, and if that's the case, then naturally that table wouldn't be of use. So we need something more fundamental, something more helpful. What we do, in fact, is that, so while this enthalpy of reaction and enthalpy of combustion was what I introduced, and it had its limitation, if we introduce something called enthalpy of formation, HF, then the difference is that I also, as part of the enthalpy of formation, I'm going to assume that the basic gases, and by that I mean these four gases, oxygen, nitrogen, hydrogen, and carbon, will also have a value of 0, retaining these standard conditions, which I said earlier. Then this allows me to then find and make it more uniform, because the limitation that I mentioned about combinations of fuel and so on will then disappear by making this assumption. You will see this more detail in the table that I'll show you next slide. So let me just show you this, and then I'll come back to the previous one. This is the enthalpy of formation. This is the table which is now practical to give you. Let's just spend some time to understand that. First, ignore these two columns in green. I used to teach this as part of the chemical reaction, but then I decided to put them in optional reading, which means we're not going to deal with them, but you're more than welcome to go through them and read them, and I'm sure majority of you will do that. Not really. So if you look at what I want you to use as far as this unit is concerned is this column there, enthalpy of formation. The stable elements which I talked about, naturally they are 0. They're given the value of 0. Then the rest of them, you will then see a number of values in there, sometimes positive, sometimes negative. The negative ones are the exothermic ones. And this is what this slide is talking about. When you are releasing energy, such as the CO2 which I mentioned, this becomes, at least in our reference, becomes negative because it's leaving the combustion chamber. And when you're providing energy, then it's positive. So any value you see in here in terms of negative, that is, in fact, I've mentioned this here. Negative is exothermic, positive is endothermic. Majority of them are negative anyway, but that is exactly what we then are going to use in order to then work out, for example, what happens or how much energy can you extract or how much energy you need to provide to your process. There's something, I promise you this is the last part of the whole enthalpy formation, because there is something called the heating value, which is very similar to the enthalpy of combustion, but it's really the absolute value of that. So it doesn't really distinguish between exothermic and endothermic. And that is not the interesting bit. The interesting bit is perhaps, well, when I say interesting, as far as interesting as it can be, really. You've got two options of higher heating value and lower heating value. The reason why it's important to mention this is because there's a table, again, It's commonly used, it's in your appendix, and you see there are two columns for these heating values, higher and lower, as well as some common ones that you know, Cp for example, density, molar mass, and entropy of vaporization. I mean, these are, you all know these four anyway, but in order to understand what these are essentially based on the entropy of combustion, but the absolute value, as you can see here, there's no negative or positive sign. And what is the difference between higher value and lower value? Again, just comes from the water and the moisture content. I've explained this in here, in this paragraph that you see in there, but basically what you see is that the value of entropy of formation for H2O is different depending on whether it's in the vapor form or the liquid form. And if you subtract these two numbers, it's about 44,000. So when it comes to higher value and lower value, this is just referring to what is the moisture, the form of the moisture, for example. You have the higher heating value when the moisture is in a liquid form, and you have the lower value when the moisture is in the vapor form. Which is why you can see that sort of difference. Not exactly 44,000 in every case, obviously, but you will see that the higher value heating value is much higher, obviously, than the lower one, simply because of that form of moisture available. There's an example which we're not going to have time to go through this, but this will reinforce the use of the entropy formation. So definitely this is something that you need to go through in your own time, please. And I've made enough annotation to direct you to the right table and source of information.